The electric potential difference, sometimes known as voltage or PD, describes the energy transfer per unit charge in a circuit. So we might find if you are measuring the electric potential difference across a battery, you'd see that you'd see values which indicate how much energy is going into the circuit per unit charge. Or if you measured the electric potential difference across a light bulb, you might find how much energy is leaving the circuit per unit charge. The idea of energy going in and out of the circuit is perfectly acceptable and kind of what you've got used to in making measurements undoubtedly when you've done anything on electricity. Now, within topic 5 of the IB physics syllabus, there's a requirement to think about electric potential difference at a field level. Now, unfortunately, the design of the course means that this requirement comes before topic 6, which gives a full understanding of how electric fields work. So quite often many teachers, myself included, will delay this kind of mention and definition until after fields have been fully discussed. So let me explain why. So you'll probably have an idea, okay, you understand what voltage is. Now we're looking for this definition which requires an understanding of fields. So start off with, before electric potential difference, I'm going to think about electric potential energy. Now, the statement, to move a charge from one point to another in a constant electric field, a force must be applied, therefore work is done. Now, here, if I had a positive charge Q and I moved it from A to B, what I'd be doing I'd be putting some effort in and lifting up this charge, and I'd be going against the forces of created by the electric field. Now what I'm doing here, I'd be increasing the electric potential energy. So that means the potential energy of that charge, when I let it go, would be quickly converted into kinetic energy as it falls back onto the negative plate. Now, what we can do here is we can calculate how much energy change is taking place. Now we know that energy change is going to be equal to work, and work is going to be equal to force times distance. Now because we have a uniform electric field, so we've got constant electric field strength, this is quite simple in thinking that the electric field strength multiplied by the charge of the object gives us the force, and multiply that by the distance, that gives us the amount of work done. So that tells us how much energy has electric potential energy change has taken place in that motion. Now just remember here, I'm using the example of a positive charge and I'm moving it from position A to B, so I'm actually increasing the potential energy. Okay, it's just something to note when you think about that. If the charge was negative, or the direction of the field lines were switched around, or this would have an impact on the sign relating to the energy, something you should be very careful of. So that's the idea of electric potential energy. That's the energy side. Now, potential difference, as we know, is the amount of energy per unit coulomb. So let's think about this now. Let's talk about this in a little more detail. So the electric potential difference. This is the difference. Electric potential difference is the difference in electric potential between the final and initial location when work is done upon a charge to change its potential energy. So what we have here is, if we work out that potential difference is the amount of energy per unit charge, so therefore the work done divided by charge. Now in this case, the work done, as we just saw, is going to be the field strength multiplied by the charge times by the distance. And we divide this by charge, so clearly the charges cancel out, and therefore the electric potential difference, change in potential energy per unit charge, is going to be the field strength multiplied by the distance between one point to another. So that's what the voltage is going to be equal to. Okay, so the electric potential difference is going to be equal to the field strength times by the distance. Now I'll try and show a problem now and I'm trying to answer some questions to get you to think about it. So here's the problem. A charge of plus 10 microcoulombs is moved across an electric potential difference of plus 150 volts. Okay, so that's the opening statement. I've got a series of questions which I want you to think about. Okay, and I'm just going to be filling in the blanks, nothing more. But hopefully you'll be able to do this ahead of me. Will the charge accelerate on its own, or must the charge be forced to move across the electric potential difference? Now, as we know, what we're going to do here, by moving from A to B, it must be forced, because you're going against the electric field. As the charge moves across the electric potential difference, it will receive, well, how much will it energy per coulomb will it receive? Well, what it's going to do, it will receive 150 joules per coulomb, so that means it will receive the electric potential difference, which is defined, and this is going to be found in the form of electric potential energy. So for every coulomb of charge there's 150 joules which is going to be gained as it moves from one position to another, that potential difference. So this obviously means work is done to move the charge from an area of, and here we've got to think about, we're going from low potential to high potential. And the work is equal to 0.015 joules. Now remember here that we've got 150 joules per coulomb, and we can multiply this by 10 microcoulombs, and that gives us the Z value for 0.015 joules, the amount of energy. If the charge is released, its energy is going to be converted. So this is equivalent to a ball falling if it's let go. So what's going to happen is it's going to be converted to kinetic energy as it moves to an area of lower potential. So it falls down through the field. I'm always kind of like wary of using the falls down terminology. It fits this description and it fits this diagram, but remember, just because it's going down, you've got to think about the direction of the electric field taking place. When the charge was moved across the electric potential difference from high to low potential, it gained 0.015 joules, because that's equal to the work done. So that's the idea of electric potential difference. Another thing which is mentioned here, I should talk about now, is the electron volt. Now, the electron volt is a unit of energy which is quite often used in these situations. The reason for that is an electron volt is the energy gained by one electron moving through a potential difference of 1 volt. So let's think about how many joules that is. If we have potential difference of 1 volt and we have 1 electron volt, this means that 1 volt multiplied by the charge is going to give me the work done. So what I have here is 1 electron volt equals 1.6 times 10 to the minus 19 joules. It's a very useful unit if we're just thinking about an electron moving through a field. So I'm going to end up with a final question, so it's kind of hopefully join these things together. Calculate the kinetic energy in electron volts and the speed of an electron accelerated in a vacuum by a potential difference of plus 1000 volts. Okay. So, give you a moment to think about this, and we go with the solution. We know that voltage is the change in energy divided by charge. We know that the kinetic energy of the electron is therefore going to be voltage multiplied by the charge on an electron. So that Q previously we recognise is actually going to be that of an electron, the charge on an electron, and we recognise the change in energy is going to be converted into kinetic energy in this situation because the electron is being accelerated. So having rearranged and just renamed that, it means that we can recognise that 1000 multiplied by 1.6 times 10 to the minus 19 gives me 1.6 times 10 to the 16 joules, or 1000 electron volts. The kinetic energy, that's calculated. The speed, so here this is an idea, if we know how much energy it's gained, and we know the mass, therefore it's the only unknown is going to be the velocity. So what we can do is rearrange for v squared and then find the square root of that. It's going to give me an answer of 1.87 times 10 to the 7 meters per second. So that's electron potential difference and also the electron volt, which should now really wrap up your understanding of topic 5.